thank you for switching rooms and everything. Please note that this is a magical moment because I connected to 2 different projectors and both worked on the first try via HDMI and USB-C. So, and I'm on Linux. I mean, please, if you can defrag the empty spots. So if you have an empty spot next to you and you're sitting on a corridor, please switch towards it so we can free some spots. I'll try to walk on the stage so that people behind the column can still see me. I have to first thank GoLab Conf for having me and to being yellow, because yellow is my favorite color, and sadly there aren't many yellow gophers around. So, if anyone wants to follow the slides from the phone or from their devices, this is the QR code that links to this slide deck. So, instead of taking pictures of the slides, you can just take screenshots, which are usually clearer. Little bit about me. In my time, I'm an open source developer as much as I can. I used to be a penetration tester and code reviewer, and I'm now a security engineer at Google. And sometimes I write some stupid, funny, or basically ranting stuff on the blog that you see here. I always like the fact that my computer has more than one CPU, because it allows you to scale and to do stuff fast and to do stuff asynchronously. So while you wait for something, you can do something else, and while you do something else, you can do even more things. And the thing that brought me to Go was exactly this, a native support for concurrency. And I saw that all the hassle of other languages, of doing async stuff, wasn't there. How many here have had issues with calling an async function in a synchronous way or vice versa? I mean, like, I spent so much time trying to get the result from an async task in C# or something like that. It's like having functions that hate each other in the language, and you have to do that in a certain way and do that other thing in a certain other way, but you just want your result. And Go just takes away this problem. So I connected to a Wi-Fi. Okay, so I decided to give it a try. And that was 3 years ago. And I said, well, let's try these Goroutines. Let's try how they work. And this was my first snippet of Go. Now, who wants to try to guess what is the output of this code, which is a counter from 0 to 9 included, a go, and a println. It's just 3 statements. Who wants to try and guess? Who says the output is this one? No? Okay. Who says the output is non-deterministic? Raise your hands, please. Who says the output is deterministic and it's not that one? Okay. So this talk is about the few surprising things in Go. Because Go, as Cassandra said, is not supposed to ever surprise you. Sometimes it crashes. So yeah, that's interesting. Well, what? Close and rerun. No. Well, the output of this function is 10 times 10. It's just 10 times. So my reaction to this was, of course, what am I looking at? Why is this thing going up to 10? Because remember the loop was including 9. And why does it just print 10? And sometimes you can get a 7 or a 5, but most of the time it's just 10. So what happens there is that what I'm calling is not a function, it's a closure. And closures are special kind of functions that, given the same input, can return different outputs, which is the opposite meaning of the word function. A function is supposed to always return the same output for the same input, closures don't. So as you can see behind me, I have a free variable called freevar that contains the string hello. And a closure, a simple closure, just prints it plus concatenated with the parameter. The output of the code, which is first hello closure, and then I set the free variable, and then I call the same function again. You see, I'm just calling the same function the same way. F closures, F closures. What it ends up being is that it will probably not run, of course, is hello closures and goodbye closures. This was one of the first things that surprised me because the languages I came from didn't have closures, and that was the first surprise. But also there is a problem with the concurrency. The Go runtime doesn't know what you're trying to make it do. It just sees your code and tries to optimize it. So if you see, there is a statement that runs multiple times with a variable, which is the for loop variable, which is changed at every iteration. And what the runtime sees is that you're doing stuff with the variable, and there is a loop. So the runtime tries to make you faster. And if the runtime sees you writing a loop, writing something that computes and spawns and does stuff, why would ever interrupt in that point? Doesn't make sense. There's a loop that does stuff. The runtime doesn't want to pause you, doesn't want to make you slower, so keeps spinning. The for loop keeps executing until the end, and then the long queue of goroutines that have been piling up are allowed to run. So also the example that I showed you before prints to the standard output. Printing is a syscall, and Go knows that a syscall is slow because it requires a context switch, it requires a lot of burden, depends on the operating system, sometimes it can take up to milliseconds to just print to a standard output. So it doesn't want to do that until it's necessary. And that's what I was observing. So my first snippet of Go had two pitfalls, and it advertised itself as a language that never surprises you. So I was like, maybe, I don't know, let's keep going. After a while, I found out that that was basically one of the few surprising things in Go, so I was happy about that. And I tried to write a checker, a static checker for that kind of pattern, but it's not that easy. Because, as I said, there's a difference between syntax and semantics. And when the language tries to understand your semantics, that's where things get messy. So here are some patterns that you can have in your code that might be valid patterns, stuff that you intended to write that way, that a checker would recognize or not recognize as a problem. So this is not as easy. I mean, unless the Go statement is the last statement of a for loop, closuring the variable, you can't really understand what the coder meant to do. If the last statement is a Go statement, you probably have a bug, if you're closuring the loop variables. In all other cases, like the last one, there is a for with a variable, and then a Go func that uses that variable, and then something that either waits on a channel or panics if something goes wrong. This is valid code. I mean, why not? And the checker that I tried to write, of course, found this as a false positive. So this is something that you have to do by hand. Be sure you never closure the loop variable. And channels don't help you in that. Channels are supposed to help you with thread async and all the parallel stuff, concurrent stuff. But they don't in this case. The code behind me takes a queue, which is a channel of HTTP requests, and then ranges over it. And for every request, spawns a new goroutine handling that request. This is potentially valid code that you might have somewhere to just schedule the incoming request for HTTP or gRPC or anything that you like. But this is closuring request, which might lead to giving the wrong answer, the wrong response to a request that a hacker might send in. so you don't want to give the wrong answer. The fix suggested by the Go team in effective Go, the Go way to do things, is to add a very, very odd fix, which is redeclaring the variable. So sometimes if you end up in your code, on the code that someone else wrote, and you just have a variable colon equal, the same variable, they might have ended up trying to fix this problem. And this is one of the least readable pieces of Go that you can end up with. This is rescoping the variable to an internal scope, so that the garbage collector now knows that the reference is not the shared one, but is a new one for every loop, for every iteration of the loop. So it redeclares the variable once every loop, and that saves you. This is not very nice, but this is the way to fix it. So I don't want you to do it now, but if you go through your code and you find something closure in the loop variable, you might want to add that line, because debugging these kind of things is not nice. Believe me. After that, I was like, fine, let's try out this language. And I wrote for a year without encountering any other surprising or problematic stuff, until I found some weird behavior. And I decided to say, okay, I'm seeing more weird stuff. Let's find out what's going on. How many here know anything about the MGP model in Go? No hands? Okay. When you spawn a process in Go, it finds out how many CPU cores you have, or how many virtualized cores you have in case of hyperthreading. And it spawns as many operating system threads. No more, no less. Sometimes 1 or 2 more, depending on the architecture. But basically, if you have 10 cores, you're going to have 10 threads, even if you spawn 1,000 Goroutines. Then for each of those cores, virtual processor, which is called P, is spawned on top of it. So for each physical OS threads, there is a Go processor that is going to schedule your Goroutines, to run your Goroutines. A Goroutine cannot run until it gets the attention of one of the processors. Then there are Goroutines which are in queues, and they are appended to the processors. So if a Goroutine wants to be executed, they queue up. And the next time a processor is going to be free, they're going to draw them from the queue and execute them. If a processor ends up having no Goroutines left to execute, it can steal Goroutines from the other queues. So this creates some sort of fairness, because you don't waste computing time. Processors never sleep. They just still work, if that's a thing. They still work from the other processes. This is very nice because it reduces contention. Because scheduling across OS threads is very costly. Scheduling across Goroutines is basically free. It's just an atomic right. So this makes your program more effective, but creates some issues. Your Goroutines are not threads. And if you have coded with threads in your life, you're used to the fact that at a certain point, your thread will be scheduled away. So you are doing something, and someone is going to come in, usually the operating system, interrupt you and say, you're done, and I'm scheduling this new guy on this core. And you're like, well, fair. I mean, they have to do their job too. Goroutines don't work that way. When you compile your Go code, statically, at compile time, the compiler decides when your Goroutine can be interrupted. It can't be interrupted everywhere, just in some points. Which means a Goroutine is only done executing when it says it's done. It has to explicitly yield execution in order to be preempted. Which in turn causes problems because you, programmers, don't know where those checkpoints get introduced. When a Goroutine time is up, is flagged as preempted. But that's it. The runtime flags it, you're done. The next time you encounter a checkpoint, yield execution, which means it can be in a nanosecond or in 100 years. The runtime, well, it's usually less than 100 years. But the runtime doesn't know. And in order to perform a garbage collection, for example, all goroutines need to be asleep. So these might lead to some problems. Garbage collection nowadays is basically synchronous. It can perform some analysis while goroutines run, but in order for a garbage collection to complete, at least once, all goroutines have to have yielded execution once. So let's say you have 10 goroutines, the first 5 go to sleep. When a garbage collection happens, the garbage collector can start working on their local variables and free some stuff. The algorithm is amazing. And then the other 5 go to sleep, and the garbage collector can finish their job and do some things across those goroutines. But at least once, they all need to yield execution. Now, read this code and try to guess the output. Now, the possibilities are, well, there is a loop with an I variable that I have declared outside of the code that you can see. So there's a trick here. The I variable is declared in a code that you can't see. Now there is a println. I invoke the scheduler explicitly because I needed to make the code fit in a slide. And then I invoke a garbage collection. Now, the two runtime functions might seem scary. They just happen all the time. The scheduler is invoked basically every time you invoke a function, and a garbage collection is invoked every time you allocate or free some variables. So this is the code. The question is, does the done word get printed? So, who says yes? Raise your hands. We have some hands, okay. Who says no? Okay, can we do a blank check? Can you all raise your hands, please? Okay. Okay, so it wasn't a hardware problem. Okay, so, good, I'm in debugger mood. So, I would like for this to function or work, but it doesn't. So, yay. And doesn't even do anything. So, the word done is not printed. This code loops forever. It never yields execution because the I variable is a byte. Now, I'm showing you this snippet of code because it's the smallest example that I could find in an open source project that has this problem. The I variable was declared several lines before the for loop. And I was going through this code and I was trying to debug it. It was a JSON parser. And I was trying to understand what was going on because at a certain point, while debugging, I was using pprof, and I saw a garbage collection start and never end, just an endless garbage collection. And what happens here is that the for loop is a tight loop. The for loop does not contain a checkpoint. So that goroutine shares a variable with the main because the I variable was declared outside. What happens is that the garbage collector starts and says, okay, what do we have here? We have the I variable, and that's about it. Is it free? Is anyone using this? Because the main is not using it anymore. So is that goroutine using it? I don't know. Can you please stop executing so I can do my work? And that's basically it, because the goroutine will never yield. It will just keep looping, keep doing its stuff. And the amazing thing is that that code worked everywhere because I was usually an int. Only in this point it was a byte. And that's it. You might not expect it, and it's just going to break your code forever. And this is also not an easy issue to solve, because the deadlock detector will not detect this. The deadlock detector can only detect dead locks. This is a live lock. Some work is being performed. There is a loop working. It's doing something. So the code is not technically dead. It is semantically, but it's doing stuff for the runtime. So if you're used to see a panic when you encounter a deadlock, this doesn't work here. It doesn't apply. And also, the runtime cannot see the future. The runtime cannot see if the code path that execution reached will eventually end up in a checkpoint, because that's the halting problem. You don't want your runtime to try and solve the halting problem while you work in production, because that kind of takes up some of your CPU cycles. The consequences is that you have an endless computation that doesn't ever yield execution, and your goroutines are just asleep, like, I don't know, playing Candy Crush, doing something else, nothing useful. And you're done. There are some tricks that you can use to debug it. So if you send a SIG abort signal to the runtime will print the stacks of all the goroutines. So instead of sending a kill, you send an abort signal, you get to the point where everything was executing. Which is nice in general, but in particular with this problem, you see where stuff is stuck. In this case, it was stuck at line 11 of main, which was my for loop. To fix this, is that you have to think about your checkpoints. It's not something that is needed every time, but sometimes when you see very long garbage collections or endless garbage collections, you have to think about it and find the points in which you should add a checkpoint. Now, there are several ways to do that. Reading from a channel inserts a checkpoint. All select statement, go statement, everything that interacts with the runtime. Syscalls introduce checkpoints. You can explicitly call the runtime. I suggest not to do that because kind of ends up being unreadable. So if you do that, add a comment. And you can ask the compiler to not inline a function. And if a function is not inlined, when it's called, the runtime is invoked. So this is the least readable option. Don't do that. There might be more. These are the ones that I found nowadays in the runtime. And I suggest reading the runtime because it's very good code. At this point, I was like, but wait, the go statement doesn't give me anything in return. The go statement is just a statement. It doesn't give you a pointer to a goroutine. So how do you stop it? Well, it's easy. Before Go 1.6, you had to pass a channel. And now we have context, and we can cancel the context, and that comes in handy. So you have no way to kill a goroutine. The goroutine has to terminate explicitly, and you probably all know this because you write Go. So as the standard library creators, they were supposed to know that, right? So this is a timeout handler. This is a standard library HTTP package that tells you timeout handler returns a handler that runs the handler that you give with the given time limit. And when I saw this function, I was amazed because I thought, hey, maybe there is a way to interrupt a goroutine from running. Turns out there's not. And this is a problem because the API doesn't accept cancellation, doesn't accept any information. So the Go team had to add context to the request so that now you can listen for context cancellation, and when the time is up, you stop doing what you were doing. I personally don't like PHP, but this is the one thing that PHP does better. It's less efficient, It doesn't do a lot of stuff, crashes, doesn't give you types, it's meh. But if you set a timeout limit for executing, this will be respected because it uses OS threads, and you can kill a thread. That will probably destroy your memory layout, and the garbage collector will be crazy trying to find out if you're still using a variable, but you don't care about that because you're writing PHP. So, the timeout handler used to be like this about a year ago. Then someone pointed this problem out, and it became like this. And to make it fit into a slide, I omitted some code. I removed part of the code. Because now it listens for cancellation and tries to cancel the context and does a lot of stuff, and then has more timers. It has to replace the context that is inside the request to have a context with cancel, and all that kind of stuff. Because as I said, you can't kill a goroutine, you just can suggest it to die. But at the moment in the language, there is no way for this code to check if the goroutine that is running, the handler, will actually listen for cancellation. So this function still doesn't know if the called function will listen for cancellation, which means that when they updated the standard library, they had no way to tell people to update their code accordingly. So if the vulnerability was there, it's still there. This just now helps you, but actually doesn't make you write good code. And there are more examples of problems in the standard library, like the Walker interface. The Walker interface is good and nice when you have to go through a directory in your system. It has a small problem which you see highlighted here. Walk can be inefficient. And what I want to see, if there is something inefficient, is a way to abort. This is the way I like my APIs, abortable. I don't like stuff that you just call and you hope it will eventually give you back your control. I want to have control on the code I'm writing. I'm writing it. The Walker interface does not give you that because it doesn't accept context. It doesn't accept a channel. It doesn't accept anything. So you have to do it yourself. Go the old way, and closure, because we like closures, I mean, they're predictable or not. Well, you have to closure a context inside the function that you pass to the Walker. And then, when the context is cancelled, you have to return an error. So, since Walker accepts a function, you're able to make it interruptible. There is no other way, no other good way. And I mean, if you're browsing a local directory, this might be acceptable to not be interruptible, but I mean, that interface is over FTP. So if you're browsing a very deep FTP tree, you don't want your server to go down because, I mean, there's a garbage collection going on just because the remote server is not responding. I mean, you don't want that. You would like to be able to say, if it takes more than 5 minutes, just kill it. And this is the way to do it. So for every standard library function that accepts the functions in their interface, you have to closure a context. Because the standard library was designed where context, when context was not in the standard library. There are some functions, like HTML.parse, that don't do that. And then they don't give you a function, and then don't accept a function. So if you're trying to parsing some HTML, you might as well get the Candy Crush back and start playing, because sometimes that will never yield execution. Wrapping up, always check your scope, and if there is a closure variable, make sure you redeclare it. Make sure you put the checkpoints in the hot paths that might end up being tight loops. And remember that you cannot kill a goroutine. You should not kill a goroutine. There are ways, but don't. Check for cancellation. When you design your API, please check for cancellation, always. If you write a library in Go that I'm trying to use and I don't see any way to cancel the calls, I'm not going to use it, because it's unreliable. So carry along the context. It's just one parameter. You can just not use it if you want. Use context.todo to test it. Just have it there. And if you're trying to use a library that doesn't have that, add it yourself or submit a PR. Now, this is the QR code for the slides. I'm gonna accept questions now. I hope I have the answers. If I don't, I'll try to respond on Twitter. The next slide contains a lot of useful links that I didn't paste in explicit mode, so the only way to visit those links is to click on them. So this is useful stuff. There is a bug tracking this issue, so the Go team is reacting on this, and they're trying to find a solution, but it's not there at the moment. Thank you. Any questions?
Generally speaking, and thanks for this, it's very useful. Generally speaking, what are your advices to avoid Goroutine leakages? Like, using buffered channels or closing the channels from another Goroutine, design practices and coding practices that can help avoiding such issues.
Okay, my solution for that is every time you write Go, so every time you use a Go statement, you have to have thought about the way to kill it. So before you write Go, you have to have some code that gives you the control on how to kill it. There is no syntactic sugar to help you do that, but that's the way I usually do it. And that's the well-known best practice to do that. So before you start a Goroutine, you should have prepared the way to kill it. Okay.
So I've run into a lot of the same problems that you talked about, and do you have any thoughts on what could be changed in the design of the language in a future version to alleviate some of them?
So there are some proposals to make the runtime preemptive that might be transparent to you. So even in Go 1, we might have something like that. I'm following a couple of issues that are tracking changes for Go 2 that plan to add a syntactic way to say how to schedule and how to close a Goroutine. They are probably going to be rejected because that is a very complex thing to do. And you don't want the garbage collector to have a handle on when to free the resources taken by a Goroutine or kill it. It's not an easy issue. The Go team is working on that. But at the moment, I haven't seen a valid solution to the preempting problem. To the closing problem, there is context. So we either pass it explicitly or maybe we embed it in somewhere in Go 2, but the point is closing has been solved, preempting, not yet. Anyone else? Oh, okay.
You may have already mentioned this, but are there pitfalls to watch out for passing a context into a closure in order to cancel the Goroutine?
Mm-hmm. Sorry, what is the question?
So you mentioned we should always avoid passing in a variable into a closure that is a Goroutine, right? But like, if you're passing a context into a closure, like, is there anything to watch out for?
Well, yes and no. I mean, when you pass a context, the only thing you're supposed to do afterwards is close it, or cancel it. You should not modify it while there is someone having the same reference to the context. If you want to do something else with the context, you are probably going to use something like with value, or get the value from it. And those are concurrent safe. So the standard library makes sure that if you call with value on a context, the new context you are given is not going to break someone that is using the previous reference. So context is safe to pass around. Well, if you close it, it changes the behavior. Everything else is safe. OK, thank you.
Thank you.